With all these definitions, we can finally fully state, the fundamental theorem of linear algebra. In Chapter 2, we built up our concepts of column space, meaning like the range space of a matrix A or a linear operator L. And we also talked about, a little bit less, but we defined the row space, which is the span of the rows of a matrix A. Also, called the range of the transpose of the matrix, since the transpose changes rows to columns and columns to rows. So now, there's the fundamental theorem of linear algebra is explained on the handout in all its glorious notation. Let me give you a more concrete picture on the whiteboard. But before I hold that up, I want to encourage you to read that on the handout. Practice your reading skills. Notice things like L star. The star is the complex version of transpose. And so if you see range of L star, that should translate into the span of the rows of a matrix. So now here's the picture. Let's look at a Y and an X. Let's say that Y is in the row space of a matrix A, and X is in the null space of that same matrix A. Notice A has nothing to do with this, so we're just looking at if we take these two vectors from these places, from the rows and from the null space, and do the inner product, we're going to look at what we get. Because Y is in the row space, it means that we can replace that with this combination of the rows of A. This is a transpose because a transpose says we're going to make this combination of the columns of A transpose. That means these are the combination of the rows of A. And we transpose back at the end to keep this as the rows, alpha being a row. And so whatever this representation is, however we get to Y from the rows of A, we use that transpose property, that the transpose of this product is reverse the order product of the transposes. And so the column becomes the row, and then A transpose, since the rows made up the columns, we can put it back to the regular matrix A. And no matter what alpha is, this is where we use the property of Y. Here's where we use the property of X. If Y has this property and X has this property, then it doesn't matter what alpha is. Because X was from the null space, AX is 0. This is a picture of, for the case of matrices, this fundamental theorem of linear algebra, that the row space of a matrix, which seems like it should have nothing to do with the columns, is actually the orthogonal complement. We haven't shown complement here, but is at least orthogonal to everything in the null space. It doesn't matter what Y and X are. We know that whatever Y and X are, they have these properties. Anything in the row space is orthogonal to anything in the null space of a matrix. So the place to box on this handout will be at the bottom of page 2, where it says the column space of A is equal to the left null space of A orthogonal complement. That last centered equation. That's basically, that is what we want to box on this handout.